we were discussing characteristic functions. Okay, so this is how it is defined. If we have a random variable, x is either discrete random variable or continuous random variable, any random variable, then the characteristic function, which is a function, it is a function from real line to, it is just complex numbers. So phi x at t. So we can define expectation for complex valued random variables. It is I t x. That's all. Okay. E power I t x. This is the characteristic function of x. So we want this characteristic function is used as a tool to study random variables, to prove properties about random variables. We prove it through. So this is a complex valued function. Of course, t is a real valued function. We know that this is defined for all t. Okay, expectation e power I t x. This has modulus 1. So this is defined for all t. So this is a well-defined function on R, and it takes values in complex number. And some of the properties, so if it is x is discrete, you can write it discrete, and if it has a mass function, this is the mass function, okay. Then phi xt equal to summation f of, whatever. The sum, it's a countable sum, but it's an R. It's in real line. Okay, f of x, f of x, which is just the probability of x equal to x, and e power I t x. So if x is continuous and f is density function, if that is mass function, this is density function, then phi xt is integral over minus infinity to infinity e power I t x small x f of x. Okay. So if it is continuous, it's integral. If it is discrete, it is the sum, which is just a countable sum. This is non-zero only for countable. So properties, we have already seen it. I'll just 1 phi of 0 is 1, that's clear. Okay. And mod of phi of t is always less than or equal to 1 for all t. So this is clear. Okay. It's always less than or equal to 1. That's because mod of phi of t equal to mod of e power, e expectation itx, which is less than or equal to e of mod of e of lt, which is equal to 1. Okay. Mod of expectation is less than expectation of the mod. Because of that, that's true. Phi is uniformly continuous. You know what is uniformly continuous? So, in the definition of continuity, given epsilon, you have to find a delta or something. That delta can depend on the x. It will depend on epsilon, of course, and it can depend on the point also. It shouldn't depend on the point. So we will see. So we have to talk about phi of s minus phi of t, or we can talk about this phi of t plus h minus phi of t. Okay. So the given epsilon, we have to find the delta. That's that this mod is less than epsilon, given that h is less than delta. Okay. And given epsilon, we have to show that this is less than epsilon, provided mod h is less than delta. That should not depend on the t. That's all. That's uniform continuity. So this is equal to mod of e power I t plus h minus maybe I can directly write, I hope, because integral mod of the integral is integral or expectation, doesn't matter. Write expectation. This is less than or equal to expectation of mod of e of it plus h minus e power it x. Okay. Okay. Now that is equal to, you can take the e power it outside. So this is just equal to mod of e power it, I hx minus 1. Okay. Now this is either it is sum or integral. If it is discrete, this will be a sum. If it is continuous, this will be an integral. Okay. e power itx is mod 1. I have taken e power itx out, and that is mod 1. Okay. Maybe I'll write it here. E mod of e power itx into e power ith minus 1. Okay. So mod of this is 1. Okay. So either it is this sum or this is integral. Okay. And we want to talk about, we want to talk about the, the limit h. It's basically, you are going to take, this converges to this, right? E power ihx converges to 1 as h goes to 0. There is no t here anyway. Okay, there is no t here. T is no more. So the delta will be uniform. Whatever the delta you get is uniform. So this will go to, as h goes to 0, this will go to 1. Okay, then you can find h which is very small, so that this is less than epsilon. But you have to take the limit inside. That is true because this is, this both these things is less than or equal to 2. See, we have, if we have a summation limit of something, if we have some limit of summation something, okay, equal to summation of the limit. Okay, if the inside is absolutely summable, or it's here, what happens is the following: we have this e power ihx minus 1 is less than or equal to 2 for all h. Uniformly over h, it's less than or equal to 2, and 2 is integrable. Constant function is integrable, constant function is integrable or summable, absolutely summable. So you can take the limit inside. Okay. This we will use again and again, this fact. If you have some summation of some summation over n and g n m, okay, and you have limit m going to something, you can take the limit inside, provided this is less than or equal to something, something which is absolutely integrable for all m. Okay. Or similarly, if you have an integral of two variable, and you have some limit, or you have a sequence inside, you can take the limit inside, provided that's uniformly bounded by an integrable function, okay, for all of them. So we have discussed this before, right? So I hope you know this. So because of that, we can take the limit inside. Okay. So it's uniformly continuous. Okay. The third property is what is called positive definite. Phi is positively definite. What it means is the following: for all z1, z2 to zk complex number, t1, t2, it will look messy, but it's very easy. It will turn out to be easy. T1, T2 up to Tn, real numbers. Okay. Yeah, real numbers. And for all k, okay, summation zi, zj bar, phi of ti minus tj, okay, ij equal to 1 to, it's double summation, ij equal to 1 to n. This is greater than or equal. This is the definition of positive definiteness. Okay. We will not be using it. I will prove this is positive definite. Why I prove this property, I will tell you. I will state a theorem which we will not prove. Okay. This is just for your information. Okay. This is the definition of positive definite. That is, phi is positive definite. That is, it satisfies this. Okay. For all z1 up to zk, given k complex number, any complex numbers, given t1 up to tk, any set of real numbers, for any k, this sum is positive. Huh? Where is the inner product coming? Where is it? It has to do something with inner product, but there is no inner product in this. Where is the inner product? Inner product between what? It has something to do with inner product. You have seen it somewhere, I'm sure. But there is no inner product here. This means in somewhere some inner product is positive. That's right. But what is the general product? Yeah, but where is Bravo? I mean, that's fine. But what is the Bravo? What is the K? I mean,
and in the middle the operator
that K, something like this, right? There is no operator. It's a function. There is no operator. Anyway, you are right. But yeah, okay. This is it's a similar thing. So this is summation ij equal to 1 to k zi zj bar p of ti minus pj. This is equal to summation ij equal to 1 to k zi zj bar. P is just e power I t I mean, this I is different. This is complex number I. This is index I. Okay, please. X minus tjx, which you can write it as e power I tjx bar. I mean, tix minus tjx. That's what we get here. And there is an expectation here. Okay. That's what by definition. By definition, I have just written it like this. Okay, this is just itj bar. And this is equal to, you can take the sum inside. This is just a finite sum. And this is equal to modulus of summation zi e power I ti x square. If you take the modulus of z1 plus z2, modulus square is equal to z1 bar plus z2 bar, right? So modulus of this is this. This is I equal to 1 to k. If you take this square, this is just this times conjugate of this, bar of this. Okay, and bar is linear, so you will multiply each of them, so you will get this. You just write down or think about it, it will be clear. Okay, summation zi this zi zj bar. I mean, that will be a two summation. Yeah, summation in I and j. This is equal to that. I mean, you have to sum. There are two summation, no? If you take two of them, z1 z2 plus z1 bar plus z2 bar. Okay, z1 z2 bar z1 is like this. So there will be a ij summation, no? When you square it, there is I and j. Yeah. If you want, you call it something else. I is there, j is also there. The other summation is with j. You can't use I. Okay, you write it like this. Okay, you like this. If you want, zj, and there is expectation out. Zj, j equal to 1 to k. Okay, e power I t j x whole bar. Okay, now this is positive, so that's what I have written earlier. This is equal to modulus, which is equal to modulus of that square, and that is positive. So expectation of some positive random variable is positive, so it's positive. Okay. This is a positive random variable, whatever. You have a x here, so it's a random variable, function of a random variable, and it's a positive random variable. Expectation of positive random variable is positive, so it's positive. So any complex number, any real numbers, this is positive. This is what is called positive definiteness property of the characteristic function. Okay. So why we do this is the following. There is a theorem called, we will not prove this. It's called Bochner's theorem. I'm just going to state it. Okay. If phi is a function from R to C such that phi of 0 is 1 and 1 and 2, phi is continuous is enough. I mean, uniform continuity will follow. And 3, phi is positive definite. Then there exists a distribution, Bochner, Bochner. Yeah, you can call it anything you want because I may not be calling it the right way. So Bochner or Bochner, okay. Spelling is correct. Okay. So positive definite. Then there exists a random variable somewhere. Okay, maybe not random variable, but I mean, if it is discrete random variable and the mass functions are same, if it is continuous, we haven't proved that density functions and random variable are same. We haven't proved. I mean, there is something you have to prove the existence for uniform. You have to use measure theory to do that for uniformity. But what I mean is, then there exists a random variable or whatever random variable such that random variable x such that phi x of t, such that phi x of t equal to this phi of. This is just the converse. Okay? The characteristic function satisfies these three conditions. These three conditions, I mean, you know that density function, there are some properties. Okay? It integrates to 1 and it should be greater than or equal to non-negative. Then it's a density. Like, and distribution function has a property. It minus infinity, it's 0. At infinity, it's 1, and it's right continuous, increasing, all that. Then it's a distribution function. Similarly, this is the property which determines the characteristic function. If something is satisfies these three property, then it is actually a characteristic function. We will not prove this. Okay, it will be more difficult. We will anyway going to prove something difficult, so this will be much more difficult. So we will not prove it. Okay. Okay. But instead of this, this is some. I mean, this what this says is something like you have a collection of density functions, or I mean, you have a collection of distributions. Okay, I mean, distribution can be either continuous, discrete, or a combination of both. You have a collection of the space of distributions. On the space of distributions, you take have a map f going to phi f. Okay, you have a characteristic function associated to that. This says that that's surjective. I mean, here you have something. This says that this is surjective. I mean, this map, f going to phi f, okay? F going to a distribution function going to a characteristic function. This map is surjective. Given any function which satisfies those conditions, it will. Characteristic function is all those functions which satisfies this property. No, nothing like that. No, yeah, no, there's nothing like that. It can be even combination of all that. Combination of both continuous. We haven't studied, we are not studying that. We are studying exclusively discrete or exclusively continuous. That has nothing to do with it. It's always, we have proved, we haven't assumed anything. We proved uniform continuity for anything. So it will not matter there, right? We have proved for any random variable, this is uniformly continuous. Okay? So this says that this map f going to phi f is, see this map, this is the space of all distributions. Okay, this is the space of all characteristic functions. That means the space of all functions satisfying these three properties, not anything. So given any distribution, you get a characteristic function satisfying these conditions. You get that. So this says that this is a one. I mean, the actual theorem is this map is continuous 1, 1 onto. What it means by continuous is this given. I mean, if you have a distribution Fn converges to F, okay, that is equivalent to saying phi Fn converges to Pf pointwise. Okay, we will prove that theorem. Okay, there is something called continuity. There is something called 1, 1. There is something on onto. This talk about ontoness. Okay, surjectivity. So now we will prove the 1, 1 part of it. Okay, we will prove separately for discrete case, continuous case. Okay, so this is the proposition. To prove that, we have to get an inverse. I mean, to prove 1, 1ness, we have to get back. Given a density or mass function, we get the characteristic function. Then by doing something, we should get it back. Okay, that will make sure it's 1, 1. Okay? So suppose if x is a discrete, so for simplicity, let's assume. I mean, because we have a different formula for integer valued one, better formula. Okay, because of the Fourier series and that theory. So if you have a discrete random variable, x is a discrete random variable, okay, and fx is its discrete and integer valued random variable. Integer valued, not even positive, integer is fine. Okay, need not be non-negative. Integer valued random variable, xs is the mass function, okay, and phi x is characteristic. Okay. We don't know the mass function. I mean, we know the random variable, but for somehow we compute the characteristic function by somehow. Okay. For example, for sum of the thing, we can just take the product. If you have x and y are independent, and you know the characteristic function of x and y, then x plus y you can compute it just by multiplication. But you don't know the mass function, right? So how to get the mass function? So then this fx at k, okay, k is in z. This is integer value. This is equal to integral 1 by 2 pi. You can take integral 0 to pi also, but I am taking minus pi to pi. Okay. Doesn't matter. Phi of t. So there we took e power itx, here we took minus it k, okay, phi of t. You just take the inverse Fourier transform. Characteristic function, if you have something, you integrate this with respect to, or you take, you take the expectation by with the e power itx. Here you have the minus here. This is a factor you need. Some factor will come out. Now this is the formula. Okay. If you have any integer valued random variable, and suppose this is mass function, this is characteristic function, this is how you get back the mass function from the characteristic function. Of course, given the mass function, you compute that sum, you know how to compute the characteristic function. This is how you get back the mass function from that. Okay. Proof. This is just a computation. So we compute this integral, okay, minus pi e power minus k, and phi of t, we know how to. This is just integral k in z, okay, e power k k prime, okay, f of k prime. Exactly, we will do that. Okay? Because if you take the mass, this is modulus 1, this is modulus 1, and this sums to 1. So because absolute continuous, we can interchange that. Okay, I don't have to write it. Okay, I hope we have done it several times. You take sum and integral together, and whatever inside, that as modulus is just modulus of this, and that is summable in both. That should be summable. That should be integral. Sum should be finite. Modulus of that. Okay, but that is only sum. So this is summable. So we can interchange that. So we interchange it. So 1 by 2 pi, we have this, and we have sum over k in z, and integral minus pi to pi. Huh? Sum? Km is for k prime, right? Correct. Yeah, k prime. Okay. So f of k prime, will come out, of course. Okay. Then this is just e power it k prime minus k dt. Huh? 2 pi? Correct. Yeah, you know the integral. Okay. You can just write it. That is equal to summation over k prime, okay, f of k prime. That integral you know how to calculate. It k prime, k prime not equal to k, then with with when k equal to k prime, that is just 1 inside, and the integral will be 2 pi, and you will just get f of k. Okay. When k equal to k prime, this is 0, this is 1. So integral minus pi to pi is just 2 pi. That will cancel with this 2 pi. You will only get f of k. Okay. So when k equal to k prime, it is just f of k. When k not equal to k prime, you can write like this. Then e power, the same thing, whatever you have inside. It k prime minus k between minus pi to minus pi. Okay. You have to insert pi here and minus pi there. But then I hope you know e power ix minus e power minus ix is just sine I times 2i, right? 2i, no? 2i sine x, right? Correct? Eh? Yeah, no, minus will become plus. Okay, so this is equal to f of k plus summation k not equal to k prime. Okay, so 2i will I that will cancel. Doesn't matter. You have some constant here, and then you have sine of k minus k prime pi. This is an integer. Sine of that is 0. So this is just it's 0 for huh? Yeah. Use what? But that comes from this. If you can directly use the theorem itself, no problem. Once you know the proof, you can use directly anything. Yeah. Sure, you can do. You can use. This is just a. I mean, I don't know whether you have computed complex integral. This is a complex thing, so it's okay. I mean, yeah, we are in first year, so you have to do it. Otherwise, you will just directly say that. Yeah. Okay, this is for integer value. Let us do it for general discrete value. Okay, x be a discrete random variable. Okay. Then, of course, again, fx is mass function and phi x characteristic function. Okay, then how to get it? Fx at let's say x. I mean, it will be non-zero for. I mean, it will be non-zero only for countably many of them. I believe we can use this x. Let's see. Let me state it. This is equal to limit minus t to t, 1 by 2t, limit t going to infinity. Okay, the same thing. E power minus it x. Okay, itx e power. Sorry. Then p of t. Here, there is some constant. I have written as constant. I don't care what it is. Okay, then this is 0. Okay. This is slightly different. Okay. Proof. Okay, let's do the same thing. Maybe I will go quickly. I mean, the same thing. This is f the whatever that integral. Well, let's take the limit finally. 1 by 2t minus t to t e power minus itx p of t dt that is equal to 1 by 2t. So there is a sum and other thing which I change it. Sum in x and r. Okay, there is already x there. So I have y in r. Okay, y in r. I mean, this of course only for countably many, because I mean we assume there is a mass function, so which is non-zero only for countably many. E power minus it x minus y. F of let me write it and then explain you. Okay, I'm the same thing. I'm the same computation I'm doing. Okay, so it is f of y. Okay, integral minus t to t by t. Okay, e power I t which is positive y minus x, then dt. That's all, no? That's all. Phi t by definition is this is okay. Phi t by definition is that sum, no? We have written there. Where I have written. It's there. Okay. Okay. So same thing. If you use that instead of integer, I'm using something summation over x, but it's only for countably many. It's non-zero, so this is fine. It's here. So now we have to show that for I mean, so this is f of x plus summation x not equal to y. Okay. So 1 by 2t integral minus t to t e power it y minus x, okay, dt. Okay. So it's the same thing, right? It's also clear to you. So this is 1 by 2t. You will get sine. So there is a 2 here, 2i sine by I into y minus x. Okay, so 2 will cancel sine. Wait, huh? F of y with there, yeah. Okay, f of y sine t. Okay, I'll write it. Okay, f of y plus summation x not equal to y. Let me write it. F of y, okay, sine t into x minus y by t into x minus y. There is a 2t and there is a 2it and there is a I there and there is a I and there's no I here inside. That will all cancel. Same computation except this. Okay, it's fine. You're okay. Directly you can write as you said. Okay, this is fine. Okay, this is right. So we have to show that this is 0. That's all. I mean, at least limit going to this is 0. But you have a you want to take limit t going to 0 here. Okay, but this is I mean this is density function and this is less than or equal to, this is a bounded function, right? T going to infinity, I have to take, okay, limit t going to infinity. Okay, this is of course there is no t, there is t here. You can take it inside because this is a bounded function, right? I mean, when it is away from 1, it's bounded. Otherwise, or you can see it, you can expand it around 0. You can expand sin x by x around 0. This will be x times cos some theta, I mean, some number x prime, which is between 0 to x, I mean, by Taylor's theorem or mean value theorem, something. No? Cos is the derivative. Sin 0 plus this. Okay. So by x, right? No, x will go, yeah. I mean, it's clear. This is sin x by x goes to 1 near 0, and because of all these things, this is bounded. So you can take the limit inside. Once you take the limit inside, this is a bounded function less than or equal to 1. Limit is here, so this should go to 0. Okay, it clearly goes to 0. Huh? Huh? Say it again. Limit t tends to infinity. I'm sorry. Sorry. Did I say limit t going to 0 here? Huh? So yeah, t going to infinity. Yeah, t going to infinity. Let's t going to infinity. T going to 0 is nonsense, right? Yeah. So this goes to 0. And this is bounded. This goes to infinity. So this is fine. Okay. So we have proved for the discrete version. Okay, discrete, general discrete version. It is just this. Now we will prove the continuous version. Okay, which will be, the proof is, I don't know, many, I mean, I took it from somewhere in Fourier analysis, slightly simplified it and did something. That you will not find it in probability book. Okay, so I will go very slowly and explain each and everything. I will spend more time on this. Okay, these things I'm sure you can find it everywhere. Okay, so this is for the continuous version. Okay, so let x be a continuous random variable. Okay, then f be the density, fx density function here, and phi x is what is characteristic function. Okay, then fx at x is equal to 1 by 2 pi integral minus infinity to infinity e power minus itx f of phi of t dt. Here it should be minus because we define through used plus for the to define characteristic function. You can either define minus for the characteristic function and take plus here, the same thing will work. Okay? I mean, how you define there, you have to be careful. It should be the other way here. Okay, so this is what we want to prove. It is just the same double integral. Instead of we changed summation and integral here, here we will change two integrals and take limit inside, do something. So change of variable and it will follow. Okay. So first notice, but one nice thing is there is something called approximate identity used in Fourier analysis. Approximate identity, I'm not going to use approximate identity. We will use our normal distribution as approximate identity here, but that's the idea behind it. Okay. So we take this function e power minus k square t square by 2. Okay. This is the normal density function. I mean, 1 by square root 2 pi is there. Okay. This is normal with 1 by k square as the variance and mean 0. Okay. So we use this function and we notice the following. Notice what? Integral minus infinity to infinity, and there should be a 1 by 2 pi here. Yeah, it's there. Okay, I have put 1 by 2 pi. That's that constant should be there. Okay, that comes from integrating this. Okay, so minus infinity to infinity. Notice e power minus, sorry, k should be down. Yeah, k should be down. Sorry. Or I can directly use epsilon. Is epsilon is okay for you? It is just continuous. Okay, this is okay. Or you can use 1 by k instead of epsilon. If you are comfortable with sequence, use 1 by k or use epsilon. Okay, so notice limit epsilon going to 0. Okay, e power minus epsilon square t square by 2. What is inside? E power minus itx pt p of t dt is nothing but minus infinity to infinity, the same thing, e power minus itx p of t dt. You just take the limit inside. Okay, or you take 1 by k and take k going to infinity. This is okay. Limit epsilon going to 0, epsilon is here. This will go to 1. There is nothing. You can just take the limit inside, because modulus of this, if you take it, this is less than 1. So modulus, I forgot, sorry. I'm very sorry. This is true only if phi is integrable. And sorry, this is very important. Minus infinity to infinity mod phi of. I'm sorry, I forgot. I mean, this is true in general, but I mean, this is not true in general. You need to assume continuity, because phi is phi should be continuous. No, so once again, sorry, let me correct. Phi is continuous. So sorry, integrability is what needed. Phi is continuous. Sorry, this is characteristic. No, in general, if you have a function, it should be continuous. I mean, in general, if you work with the function to get it back, you need continuity. X is a continuous random variable. Phi is continuous function, and this integrability condition is needed. Extra. Huh? Not between minus infinity. Not between that. I mean, further, please add this condition. This is very important. Integral minus infinity to infinity mod phi of t dt is less than infinity. Mod of that is less than infinity. It's not infinite. So what we have is, we have a continuous random variable. Fx is a density function. Px is a characteristic function. So it is continuous by definition. Okay, and it is integrable function. Okay, the integral is integrability minus infinity to infinity is less than infinity. Then this is true. Okay, then the first statement is, maybe I can just erase this. Notice that limit epsilon going to 0, this e power minus epsilon square t square by 2, and whatever the integrand I have the same integrand here, that is equal to the same integral. That's because you can just take the limit inside. You can take the limit inside because this is less than or equal to 1, and this is modulus 1, and you assume that this is integrable. Okay, and this is the whole thing is bounded by this integrable function. Okay, should I write the condition? Is it clear? Okay, it's clear to everyone. Okay, so because of that, it's okay. You write it. Okay. So that's what I want. You should ask me like that. Okay. So to be clear, you want me to write the general theorem or just this? This. Okay. The integrand is e power minus epsilon square t square by 2. Okay. E power itx, e power minus itx, p of t. To take the modulus of this. Okay. This is okay. This is less than 1. This is modulus 1. This is less than or equal to mod phi t. Okay. This is less than or equal to this for all epsilon. So this function, which is a function of epsilon and t, okay, is uniformly bounded by the single function. Okay, that's what the condition. Okay, so and this integral phi is less than infinity. Okay, if it is satisfied, then you can take the limit inside. Okay, that's the condition. This is dominated convergence theorem. If you have some integral, inside the integral, it's a function of two variables, either a sequence and something. Or some, if it is uniformly bounded by single for all n, uniformly bounded means for all epsilon, this is true. There is no epsilon here, and this is integrable. Then you can take the limit inside. Okay, so that's what I'm using. So this is clear. Whatever I have written here is clear. Okay, limit epsilon going to 0. This thing is equal to this. Okay. Okay. So now let's compute that limit. That's what we do. Okay. So limit epsilon going to 0, integral, compute that limit. I mean, this is equal to this, and we compute this limit, and that will be equal to whatever the fxx we have to get. Okay. So this is integral minus infinity to infinity e power epsilon square t square by 2. Okay. And we have then we have phi of e power I xt. Okay. E power I xt, that's fine. Then phi of t. Phi of t is just, I mean, let's write it, phi of t dt. That is equal to, if I miss the limit, it's there always. Okay, minus infinity to infinity. Okay. Then e power minus epsilon square t square by 2 e power minus itx. Then phi t by definition, this is minus infinity to infinity ix iyt. Okay, iyt. Then fx at y, okay, dy. Right? This is the definition of that. Then dt. Let me write it and then come to. Okay. I have just expanded. This is equal to this. I have just written the definition of phi of t, which is e power iyt fxy dy dt. And now, if you take the whole integral, whatever the inside the integral, this is less than 1, this is of modulus 1, and this is of modulus 1. This is a function which is integrable. I mean, integral is 1. So whatever the integral whatever the integrand you have inside the double integral, whatever is integrable, absolutely integrable. So you can interchange the integral. That you have to check. So because of that, this is equal to minus infinity to infinity, minus infinity to infinity. So we interchange dt and dy. Okay, if you interchange dt and dy, so we yeah, limit is there always. As I said, in case I forget, the limit is there. No, limit we are not. Limit we take finally. Okay, final. So maybe we don't take the limit for the time being. Okay, let's take the limit finally. Okay, because I may forget or it occupies space. So minus infinity to infinity. Okay, so e power. So I want to integrate with respect to t. So I take that inside, but there is no t here. So I write it like this: fxy. As before, this comes out. Okay, and this is okay. I take this integral fxy. Okay, integral minus infinity to infinity. I have interchanged the integral. Okay, I mean the integral is respect to dy dt. Now dt dy. Okay, so this has gone inside. This is with respect to y variable. This is with respect to t variable. E power I y minus x t. Correct. Y minus x t. Then That's all. E power minus epsilon square t square by 2 dt whole thing dy. Okay. Fine. I will just interchange the integral. Now this is equal to minus infinity to infinity fxy. It's here, and we use the we want to get rid of this epsilon, okay, so that it will come here, okay, so that this will become normal. I mean, I don't. It will be easier. See, for normal random variable, we know the characteristic function. Otherwise, you have to write 1 by sigma something sub. So just for that purpose, I use this integral minus infinity to infinity e of I y minus x. If you epsilon t equal to this, so u by epsilon. Okay. Wait a minute. Let me write e power minus u square by 2, where u is something. Then du by epsilon. Okay, dy. Okay. I have substituted u equal to epsilon t. That's all, nothing else. U equal to epsilon t. So u square by 2, y minus x u by epsilon, and du by epsilon. Okay. I have substituted u equal to epsilon t, so that this becomes something like this. Okay. Now this is equal to minus infinity to infinity fxy. This integral, if you notice, okay, there is a 1 by epsilon. 1 by epsilon. Okay. This integral is just the characteristic function of to a constant. Of course, there is a square root of 2 pi. So you get a square root of 2 pi here. Okay. So this is just 1 by square root of, if I put a square root of 2 pi, 1 by square root of 2 pi, you have this. Okay. But 1 by square root of this is normal random variable. This is just the characteristic function of the normal random variable evaluated at y minus x by epsilon. Right. So this is just phi of normal 0, 1. To understand what it means? Characteristic function of normal 0, 1 random variable at x minus y by epsilon. Fine. One integral is gone. Correct? Okay, maybe I'll write it also. Okay. Twice. I'll write it twice. Whatever we have here, this is equal to, I apply what u equal to epsilon t, so this integral is fine. Okay. Now this is equal to minus infinity to infinity. Okay. Square root of fxy, whatever I have, square root of 2 pi by epsilon. Okay. Integral minus infinity to infinity. 1 by square root of 2 pi e power minus u square by 2. There is nothing. I have same thing I'm writing, y minus x by epsilon, then du. Sorry. Yeah. Y minus x by epsilon, u by, y minus x, u by epsilon, du. What is the definition of characteristic function? What is it? This characteristic function is this, no? P of normal 0, 1 random variable. P is normal 0, 1. Which is just integral 1 by square root of 2 pi e power minus t square by 2 e power it x. Instead of x, I have x minus y by epsilon. Okay. So it is just the characteristic function of normal random variable evaluated at y minus x by epsilon. Okay. Characteristic function of normal random variable is e power minus sigma square t square. We computed in the last class. Yeah.
Characteristic function of y minus x.
Exactly. Characteristic function y minus x by epsilon. Epsilon. Characteristic function evaluated at. Characteristic function of normal zero random variable evaluated at. So let me write that. So this is integral minus infinity to infinity fx of x. We have this, and this is characteristic function of normal 0, 1 random variable. Okay. Evaluated at x minus y by epsilon, and there is a square root of 2 pi by epsilon is also there. So we know what it is, minus infinity to infinity fxx. Okay. Oh, phi is continuous. Oh, we need f is continuous. Okay, we are assuming f is continuous also, so no problem. Okay. I need the continuity of f. which is also true. F is, we should assume, sorry, F is not continuous. We assume F is continuous. Sorry, that's what I should have. It's not following. Yeah, that's what I have to assume. I'm sorry. In the proposition, I have to assume Fx is density and F is continuous. Okay, you can assume F is. Eh? We will need it after this step. I mean, since I know the proof, I know that it is needed later. Okay, Fxx and square root of 2 pi by epsilon. Okay, this you can write e power minus x minus y square by 2 epsilon square. I mean, if you characteristic function of a normal random variable is minus sigma square by 2. Huh? F of y dy. Okay. X is fixed. Okay. This is the characteristic function of normal random variable, e power minus t square by 2. Okay. Now we have all that. Now change of variable again. X minus y by epsilon equal to v. Okay. Let's say y minus x. Okay, it doesn't matter. Y minus x by x minus y is same as it's square. So y minus x by epsilon. So y is equal to epsilon v plus x. Okay, and dy is same as dv. Okay, there is a square root of 2 pi. I mean, dy is equal to epsilon times. So that epsilon will go away. So this thing is equal to, use the substitution, minus infinity to infinity, fx at epsilon v plus x, okay, e power minus v square by 2, okay, square root of 2 pi is already there, okay, dv. Right? So we have got this. Now we take the limit inside. I mean, limit can be taken inside. This is less than 1 and this is density function. You can take here fxy square root of 2 pi by epsilon, okay, and e power x minus y by 2 epsilon, x minus y by epsilon. I have called it as v. Okay, so this is v square by 2. Okay, here epsilon v plus x. Then this becomes y becomes epsilon v plus x. Yeah, and just substituting. That's all. And then of course dy is epsilon times dv, so that epsilon will go away. Okay, so we got this. Okay? I'll write here. Oh no, I haven't changed it. Okay, you can't see those things in the video. I haven't changed the camera for quite some time. Okay, maybe I'll just show this. This is what, let me explain. Yeah, we just computed the limit. We just computed that integral. We can interchange because of something, and I mean, let me just summarize what we have done. We noticed this. We wanted to prove this. X is a continuous random variable and fx is a density function. We assume that we assume that phi is integrable. Then this is the formula for this is the inverse formula. Okay. First, we notice that limit epsilon going to 0, this equal to this, because this is integrable and all that. First, we used this. Then we computed the integral. We exchanged the integral, and we did the first substitution, epsilon t equal to something, and we got this. Okay, and then we got this. Then we use the fact that this is the characteristic function of normal random variable evaluated at y minus x by epsilon. So we got this formula. Then we using this thing. We just this is because you are going back. I'm going back. Sorry. Yeah, this is this. Yeah, we just got it. And then where did I go? Oh, it's the top. Sorry. Right? Yeah. Then, yeah, this is what we got it. And then we substituted this is equal to v and change of variable, and we got this. Okay? This is what we have got. Okay, this is the original proposition. I'm sorry, I should have moved there. Okay, finally, what we have got is minus infinity to infinity, square root of 2 pi f of x epsilon b plus x e power minus v square by 2 dv, right? That's what we got. Yeah, now limit of this. Now we want to take, yeah, limit epsilon go to 0. I put t 2 pi and 1 by square root of 2. Okay. Limit, we'll take it later. Yeah, we don't need to take it limit inside. So now, exactly, when you take epsilon, yeah, limit epsilon going to 0, yeah, you can take it inside. So this is just, you now, because this is again integrable and all that. Exactly, since f is continuous. That's what I need. Since f is continuous, you get this is equal to f of x times integral minus infinity to infinity 2 pi, I mean 2 pi into 1 by square root of 2 pi e power minus v square by 2 dv. And this is square root of pi, and this is equal to 2 pi into f of x. Epsilon going to 0, this becomes f of x, and there is no v here, you can take it out. Okay, and then this is minus infinity to infinity 1 by square root of pi. So I have made the square root of 2 pi into, I mean, okay, that's I have already done here. I have 2 pi here, 1 by square root of 2 pi. This is normal density. Okay, yeah, that's one. So that's all. Yeah, this is fine. I should have recorded properly because I haven't seen a easier proof easier than this in any book. Okay. Yeah, you have seen this is easy, or you have seen this is of course easy. Yeah, this is very easy. There is nothing. But in Hoyle Portstone, it's not proved. It's only proved for normal one. And in general, I don't know. I haven't checked many books. No, our only assumption is continuous variable, and this is continuous. That's all. That is required here. I mean, in general, I don't know. Maybe no. In general, there will be something. It will be the expression is also complicated. That is what is proved. I don't remember the expression. You point of discontinuity, you have to take it into account and you have to write an expression, and that's what you will get. The theorem is true for general random variable. Okay. You can use measure and other things. Correct. Correct. Yeah. No, but we are assuming the density is a continuous function here, which is strong assumption. Okay. So the next one we want to prove is the following. Before that, we need the following definition. Okay. So this is just not about random variable, actually about distribution. We say, this is the definition. We say xn converges in distribution. Maybe I will write it. Converges in distribution, okay, to x, which we denote by xn converges in P to x, or this is also in notation. Okay. If fxn, the distribution, this is general for continuous or something, fxn at x converges to fxx at all continuous points of this, but let's assume continuous random variables on this is continuous. Okay, so at all continuous points of f, but fx. But if we assume continuous random variable, then this is not needed. This is a continuous function, that's a continuous function. Distribution is a continuous function, so we don't need. Like we will assume continuous function. Okay, so this is a theorem we want to prove next. Xn x or continuous random variable. Okay, you can imitate the proof for xn is a sequence. Okay. Continuous random variable. Okay, such that phi xn t converges to phi xt for all t. Wherever fx is continuous, wherever I mean x such that fx at x is continuous, there the convergence happens. And let's assume these are all continuous random variables, so then it's not needed. Yeah. N D distribution. This is notation. We say converges in distribution. This is a notation. Either this or this will be. Okay. Converges in the top. I put a D so that it converges in. I use this converges, then put a P so that it converges in probability or something. So it's like that. Distribution function converges pointwise. That's all. For continuous random variable. For general random variable, it should converge at all continuous points. That's all. Okay. So the theorem is if x and x they are all continuous random variable, we will prove for the continuous case. Then phi x and t suppose and phi x and t converges to phi xt for all t, then xn converges to x in distribution. Okay. If the characteristic function converges pointwise, then the random variables or the distribution function converges. That's what it says. Okay, this is equivalent to saying distribution function converges. Okay. Okay. I will not give the full proof today. I will stop at some point and then prove the remaining thing later. Okay. So proof of this. You have xn, you have x such that phi xn converges to, phi xn converges to phi x pointwise, okay, at all points. Define let 1 by k square or yeah. Again, you can use epsilon or k, doesn't matter. I use integer. Okay, epsilon. 1 by k. Okay. Let z follows zk follows normal 0 1 by k square. Okay. You define x a n equal to x n plus z k. Okay, and y k to be x plus z k. Okay, this is a two variable sequence, double sequence. This is a single sequence yk such that is this. Okay. Now, what is the density of these things? Okay, we'll stop. We'll discuss next week.